Hey everyone, I'm Shah. This is the first video in a larger series on AI agents. Here, I'll start by discussing what an AI agent actually is and why we should care about them. Then I'll review 3 common types of agents at various levels of agency. 2025 is said to be the year of AI agents, yet for many people that I've talked to, it's not entirely clear what this actually means. Part of the problem is that no one can seem to agree on a single definition for AI agents. To demonstrate this, here are some definitions from a few leading organizations. OpenAI, in their Agents SDK documentation, defines an agent as a large language model configured with instructions and tools. This is different from, say, Hugging Face's definition from their Transformers documentation, which describes it as a system where a large language model can execute more complex tasks through planning and using tools. So here there's a subtle difference. OpenAI's definition is focused on tools. That's like the main thing. While Hugging Face, they talk about tools, but they also mention planning, which is basically taking a user's query or an input, breaking the task down or the problem down into specific steps, and then executing it. And then if we look at Anthropic's definition, and so this is from a blog post called Building Effective Agents, where they define it as systems where LLMs dynamically direct their own processes and tool usage, maintaining control over how they accomplish tasks. So again, we see this mention of tool usage. However, Anthropic's definition seems to be primarily focused on autonomy, basically LLM systems that have complete control over how they do things. So I won't try to make things even worse by proposing yet another definition, but instead I want to talk about 3 key features that come up regardless of the specific definition that people might give to agents. So first and foremost, there's always an LLM involved. So in those 3 definitions we saw in the previous slide and all the other definitions I've seen, LLMs play a central role in what people are calling AI agents today. So it's going to be an LLM represented by this robot emoji and then some other stuff, some software you write around it, maybe you use a framework or you code it from scratch, but there's some other stuff that kind of augments the LLM. The next thing is tool use. So this can be something like a web search, a Python interpreter, memory, sending an email, or even access to a different large language model that is specialized for a particular task. And I'll talk about why tool usage is so important for agents on the next slide. And then finally, there is usually some mention of autonomy. So we saw in Hugging Face's definition, there was this notion of planning. And Anthropic's definition, which we'll talk more about, they really stress the importance of these like open loops, this ability for the model to reflect on its outputs and get real world feedback on them. Another thing this might include is the so-called reasoning capabilities of LLMs like DeepSeek R1 or OpenAI's O1 or O3 models. This ability for LLMs to quote unquote think before providing an answer allows it to accomplish more and more complex tasks without explicit instructions. And so everyone is very excited about agents these days. People are saying 2025 is the year of AI agents. YC is saying that vertical AI agents could be 10 times bigger than SaaS. And this might be very reminiscent to a couple of years ago when ChatGPT came out and there was a lot of excitement around LLMs and specifically building chatbots. Back then, I had people reaching out to me all the time saying how they wanted to build some kind of chatbot for their company for some specific use case. And then fast forward 1 year later, a sentiment I heard from a lot of business leaders or business operators is that they weren't able to get ROI from these chatbots. And so they might be thinking it's just a repeat of this. It's just like another hype thing that isn't going to generate return on investment. While there's a lot to unpack there, the key difference between agents and chatbots is that LLMs alone aren't enough to solve most real world problems. And so there are 2 key things that I would say make agents much more valuable than just vanilla chatbots, like the original version of ChatGPT. So the first is that agents can interact with reality through tool use. LLMs, just out of the box, they don't live in reality. They live in an imagined reality. They live in some kind of imagination land. This is why hallucinations are a big problem with LLMs. And then if you asked one of these LLMs to write you some Python code and execute it, it would just make up the outputs. It wouldn't actually run the code because LLMs can only generate text. They can't run code. They can't do web search. They can't do a lot of useful things to get feedback from the real world to make them more useful. So tools take LLMs from their imagination land based on their pre-training data and put them in the real world, kind of give them real world feedback, real world context. Another reason why agents are inherently more valuable than the vanilla chatbots we've seen in the past is this discovery of so-called test time compute scaling. And this is just a fancy way of saying that the more tokens an LLM generates, the better its responses. So this is the whole idea of giving models time to think about problems, allowing them to kind of reason about problems, come up with an action plan before giving their final answer. And so today with models like O1 and DeepSeek R1, which are trained using reinforcement learning, now we have models which are much more capable of solving arbitrary tasks without explicit instructions than before. And this ability to just one-shot novel problems is actually very valuable for agents because now you don't have to write very sophisticated and detailed prompts for specific problems. These models can solve a wider range of tasks well. And if you're not familiar with this test time compute and reasoning models and all that, I talked all about that in a previous video, which I'll link here in case you are interested. Since no one can seem to agree on a single definition for AI agents, most practitioners I talk to don't really worry so much if a system is an AI agent or not, but rather they just talk about agentic systems, basically conveying this idea that agency is on a spectrum. In other words, you can have systems with no agency, so basically like a rule-based system where the logic is hard-coded, all the way to a system that has human-level agency. And so here I'm going to convey this idea by talking about three systems at increasing levels of agency. So level 1 is an LLM plus tools, level 2 are LLM workflows, and level 3 is an LLM in a loop. So tool use is a central feature of any agentic system, and the main thing here is that tools expand the capabilities of LLMs beyond text completion. Two common tools that you might give an LLM are web search and a code interpreter. And so these two tools kind of fill in two major blind spots of an LLM. For LLMs out of the box, their understanding of the world is based on a snapshot from like 12 months ago, which was captured by their pre-training data. And of course, the world has changed a lot over the past 12 months or so. So if you were to ask an LLM about anything recent, it would basically just make something up. This is where web search can help. You can give the model access to a tool like web search, and then you can train it to identify when it receives requests where web search is going to be a helpful thing to do. Another really handy tool is a code interpreter. This allows LLMs to do a lot of different tasks. For example, doing math, which is something that LLMs really struggle with. Instead of basically the LLM trying to do the math in its head, it can write some Python code to do some complicated arithmetic, and it can send that code to its Python interpreter. The code can actually be run, and the results can be sent back to the LLM. And note, without the code interpreter, the LLM would still be able to write code. It just wouldn't be able to run it. So it would basically make up the outputs. And so these are two very fundamental tools, but there are many others that you could use. So another big one are API calls. So maybe you want to fetch information from YouTube, or you might want to connect to Gmail. So maybe you want the LLM to be able to read your emails or to write emails on your behalf. Or even you might have like a Notion page where you have a lot of notes and you want the LLM to be able to access those notes and do some kind of task that is helpful to you. And so notice the API calls go both ways. They can both be used to give the LLM real world context, real world information, and they can also be used to allow the model to take take actions in the real world, which are two essential components of agency. Another popular one is computer use. Not every program you care about has an API, basically has a programmatic way of interacting with it, but it does have a graphical user interface. So computer use enables LLMs to interact with these graphical interfaces using mouse clicks and keyboard strokes. Another tool could be another model. So for example, ChatGPT has access to a text to image model. So if you ask it to create an image for you, it can take that request, pass it to this external model, and then take that resulting image and show it to you. Another tool might be RAG. So instead of searching the internet, maybe you just want to search an internal knowledge base or over a set of documents or something like that. So that's where RAG can be helpful. And then another helpful tool is memory, which allows the system to retain important information over a long time period. So this could be over multiple LLM calls or even over multiple conversations. So while this level 1 agent of LLM plus tools matches OpenAI's definition, many people I've talked to wouldn't consider this a quote-unquote AI agent. The core limitation of systems like this is that you're basically relying on a single model and a single thread of information to solve whatever task you're trying to do. And so while this works fine for one-off tasks or small tasks, as the requests get more complicated, this can start to break down. Like for example, if I wanted a system to like end-to-end write blogs for me, so basically come up with blog ideas, pick out the best one, write a first draft or something like that, this might be hard for a single model to do well, even if it does have access to like web search to do research and a library of like past blogs and past topics or something like that. This brings us to level 2, which are LLM workflows. And so most of the agentic systems that you'll see these days are this kind of system. So frameworks like LangGraph and Llama Index are really optimized for building these kinds of agentic systems. And so all a LLM workflow is a predefined sequence of steps with at least one LLM involved. To give a concrete example, let's say I wanted an agentic system, an AI agent, to help me respond to emails. Instead of just taking an LLM, giving it very detailed instructions and giving it access to my Gmail, like the level 1 system, I might define a workflow like this to kind of make the system a bit more reliable. So the workflow would look something like this. An email comes into my inbox, then this LLM would spit up and it would categorize the email. Basically, it would see if it's junk or not junk. If it's junk, the system would move it to the trash. If it's not junk, I could pass it to another LLM to decide if it's a hard email to respond to or just like an easy email to respond to. So if it's just like a sounds great, thanks, or an email that I've written many times before and there's like a template for it or something like that, it can make that decision. Notice we could have just had one LLM do this categorization where we have one LLM that decides whether the email is junk, an easy response, or a hard response. But this is a more complicated task, so it's going to be harder for a LLM to do in just one shot. So by splitting this complex task into two simpler tasks, we actually make it easier for each of these LLMs. And maybe you don't even need to use an LLM here. Maybe you can just use a fine-tuned text classifier to do the junk, not junk, but then maybe this categorization is a bit more difficult and harder to gather training data for, so an LLM is better suited here. Okay, but then going on with the workflow, if it's a hard response, the system can just leave it for me to respond to. If it's an easy response, it can get passed to a LLM email writer that specializes in this, and then that LLM can send an email. And so the key difference between level 1 and level 2 is that we're no longer limited to just a single LLM with access to some tools, but rather we can have multiple of these LLM plus tool systems working together to solve more and more complex tasks with better performance. And so there are really countless ways you can design LLM workflows. Some are going to have more agency than others, but there's this really nice blog post by Anthropic. It's reference number 3. It's called Building Effective Agents. And there they break down various common design patterns for these workflows. So I just wanted to mention those here. So the first one is chaining. So this is like a very simple design. You have module A passes output to module B, which passes output to module C. So maybe you have a system that is going to write blog posts for you. So you have one module just coming up with ideas, another module deciding what what ideas are good and what ideas are bad. And then you have a third module that writes the first draft of that blog post. And again, you could probably have a single model do this, but it probably wouldn't perform as well as a system that breaks it into more specialized roles. Another common design is routing. So this is something we saw in the example I shared on the previous slide, where you have like this classification step and a fork in the workflow. So let's say you have an email come in and you want to classify it as junk and not junk. And that's because you want to treat these two different types of inputs differently. Another common design is what Anthropic called parallelization. So there are two kinds of parallelization. The first one is sectioning. Sectioning is when you take a task and you split it into various subtasks that can actually be run at the same time. A good example of this is, say, a user types in a request into a chat interface, and let's say to process this request, you need two things to happen. One, you need the LLM to generate a response, and two, you need to make sure the request is appropriate and abides by your terms of use or some set of rules that you have for your application. So you can actually run these tasks at the same time because they're not dependent on each other. And this will result in lower latency because you don't have to check if the query abides by the rules and then generate a response to it. You can just do these at the same time and then generate the response. Another version of parallelization is voting. So let's say you have some kind of lead scoring system. You want to grade leads as like low quality, medium quality, high quality, or something like that. But this is a pretty hard task where a single LLM might get it wrong like 60 or 70% of the time. But one way you can kind of overcome this is instead of just giving it to one LLM, you can give it to 10 LLMs, the same task of score this lead. And then you can aggregate the responses of all 10 LLMs to give your final result. The key upside here is that you can improve the performance of your agentic system, while here you can improve the speed of your agentic system. Another common design is this orchestrator workers paradigm, where instead of just having a rigid workflow like we saw on the previous slide, where basically everything was predefined and we have some agency within the LLM modules because they have the freedom to perform that specific task in whatever way they like. This may not work for tasks which are a bit less predictable, where you don't have a clear workflow for all possible requests. In this orchestrator workers design, you first have the request go to a planning LLM. This could be a really smart LLM that can reason and think through problems. And basically its only job is to come up with the workflow, to come up with the plan of solving this problem or performing this task. And then based on that plan, the tasks are delegated to separate systems. So to multiple LLMs or maybe to some predefined code components that tend to come up a lot for your specific use case. So this is kind of analogous to how you might have a single LLM think step by step through a problem and then solve the problem. But instead of everything happening within one LLM, you can spread this task among multiple LLMs to potentially get better performance. Finally, we have the evaluator optimizer paradigm. The way this works is that you have an LLM that generates some response or some output, and then you have another system review that response and give feedback. And basically this loop can continue until some stopping criteria are satisfied, and then it goes to the next step of the workflow. This evaluator optimizer pattern is fundamentally different than all the other patterns that we're seeing here. And the difference is that everything else has a clear beginning and end. It starts at point A and it ends at point B. And even if you're splitting it up to operate in parallel, there's a clear endpoint. However, because the evaluator optimizer is this loop, this could, in principle, just go on indefinitely. So inherently, this system is capable of doing tasks with more autonomy, with more agency than the other ones, because we haven't created these constraints or rails for the system to operate on. It basically figures out what it wants to do by itself. This brings us to the level 3 example, which I call an LLM in a loop. The idea here is giving an LLM real-world feedback on responses until they are satisfactory. So to give a concrete example, let's say I wanted to have an LLM system, an agentic system, write LinkedIn posts for me. So I might have an LLM writer. It's going to write a LinkedIn post for me. And then what I'm going to do is pass this post through various sets of evaluations. So the first thing I'm going to do is see if that post is similar to my existing posts, because I want it to sound like me and I want it to be relevant to the other things that I've talked about. Another evaluation I might do is pass it through a AI post detection system. That's because I don't want the post to sound like an AI wrote it. I want it to sound human-like. And then finally, I can evaluate if the LinkedIn post is actually similar to the initial idea that I fed into this LLM system. And so then each of these evaluations will have like a pass-fail. And then we can have some logic where if any of these evaluations failed, we'll gather all the feedback and we'll pass it back to the LLM writer. We might say, okay, the post was relevant to the idea, but it sounded AI generated, like 80% was AI generated, and it didn't really match the voice of my existing posts. So we kind of gather all this feedback, give it back to the LLM, and then the LLM can go, oh, okay, so I got this feedback. Here's the post I just wrote. Let me update it and write another one. And then that'll spit out another LinkedIn post. It'll go through the same evaluations. And then again, if any of them fail, we'll gather the feedback, give it to the LLM, and continue in this loop like this. And so the value of these systems is that they can perform very open-ended tasks. Let's say if I wanted an LLM to write a LinkedIn post for me, I might have to optimize the prompt for a very specific idea or very specific set of ideas for it to perform well. While it might work well on those examples, it's going to be fundamentally limited because, maybe it has to follow a certain template, or maybe it needs like a reference document to write the post from, and all these other constraints. But doing it in this way, where we're just giving the model feedback, evaluating it based on these outcomes that I care about, it can potentially figure out the best post to write through this closed loop. And then if all the tests pass, we can return the post. And so there's actually another version of this. As I'm showing the example here, we are just using the LLM out of the box, and then we're just getting very clever on how we define these evaluations to design this system. However, we could also do something similar where we actually update the internal parameters of the LLM. In other words, we fine-tune the LLM to be optimized in solving this task. So the model can get better and better the more posts that it writes. This is the idea of using end-to-end reinforcement learning on real-world feedback in optimizing an LLM system. The only difference here is that we make the parameters trainable, and then we use an algorithm like group relative policy optimization to update the internal parameters. And if you don't know what I'm talking about with reinforcement learning or group relative policy optimization, I talk about that in a previous video on reasoning models like O1 and R1. While this might sound like some kind of research project or something like that, this is actually the approach behind models like Deep Research, which is currently available in ChatGPT, and also OpenAI's Operator model, which is only available to pro users, but basically that model is capable of surfing the web, interacting with GUIs, and doing things on your behalf. Okay, so this was actually the first video in a larger series on AI agents. So here the discussion was relatively high level. We didn't go into the technical details or write any code. That's because I just wanted to lay the foundation for future videos where I'm going to talk through each of these one by one and build concrete examples of each of them. And so in the next video, I'll be building a level 1 agentic system. I haven't decided when I'm going to build it yet, so if you have any suggestions, let me know in the comment section below. Also, if there's anything else you want me to cover in this series, let me know in the comments. The AI agent space is massive and it's only growing, and I'm sure there's so many tools and ideas out there that I'm completely ignorant of. And so if there's anything you keep seeing over and over again and you think I should cover, let me know. And with that, as always, thank you so much for your time, and thanks for watching.